Okay. All right, we talked about this circular array idea, where we just pretend that after index 0, or sorry, after index n minus 1 is index 0, and it loops back over and over and over. And we could achieve this with some logic like if, but we also saw that we can use it with this modular, like that mod function, right? Where you take the remainder and basically how far over did we go? Okay, that's where we start over. That's the idea. Pretty neat, eh? Yeah, so expand capacity. With this idea of a circular array, which it's not real, it's just our fancy counting where we pretend it's circular, I could be in this situation like this. Okay? And someone brought this up, maybe it was last time or maybe the time before last time, but we know we're out of room when the next available spot is the front. Basically, when the front and rear are equal, we're out of room. Because remember, the front is the index of the first thing, and the rear is the index of the next available spot. If they're the same, we can't add any more. Okay? So here we're in a pickle. Now, in this example, this is the front. So the order is dark blue, black, teal, I don't know, and baby blue, right? That's the order. Even though you're like, well, no, it starts there. No, the front is here. The array starts here, but the start of the queue is here. So here, 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 here. Okay? We also know it's full when the count and the capacity are the same, but we also know it's full when the front and the rear are the same. So we can't just expand capacity like we did before, where, okay, double the size and then copy everything over in order. Because what would that mean? That would mean, because remember, the front is here. So we can't go like, okay, 2, 3, nothing. Index 0, 1, like we effectively added 4 empty spots in the middle of that queue. Huge problem. Is the problem clear? Yeah, so that's not going to work. So we have to be clever. Fortunately, it's really not too bad. You start at the front, go to the next thing, go to the next thing, go to the next thing, while doing that fancy modular arithmetic, because really it should be 2, 3, 0, 1 would be the order that they came from. So we have to do that modular thing where we do mod, right, that remainder. So we'll have to make sure we're doing that. But like, okay, so from the source array, the old queue would be 2, the new one could be 2, old one 3, new one 3, old one 0, new one 4, old one 1, new one 5. We're kind of all over the place. But do we see where we're going here? We would have to copy over things like this. And this would work entirely fine. Okay? You could look at this and be like, uh-oh, but there's a gap here and a gap here. That's fine because the front is 2 and the rear is 6. Remember the next available spot. So it's all fine. If I were to go in queue a new thing, it would just go here. Whatever, no big deal. So this right here is a perfectly good solution to this problem. However, we could kind of be a little fancier, I guess. Now, to call this better is not something I would say. I am not about to say that this is a better solution. I'm just going to say this is a variation of that idea that I kind of like. If you ask me why, is it better computationally, what do I gain from it? I don't really have an answer other than I just like it better this way. Where when I do the expand capacity, I go from wherever the front is in the old array to 0 here. I always reset it back where the front is at 0 to there. There's no cost to this because I already have to go through and copy everything over. I just do some arithmetic here and I can copy things over pretty easy. And don't worry, the arithmetic's easy. All we have to do is add 1 every time. And you think, but from where to where? Well, from old arrays front to new arrays 0. Old arrays front plus 1 mod length to new arrays 1. This one might have to loop back, but this keeps going. In fact, this one will never have to loop back. It's impossible. And if you're wondering why, well, remember, if this old array had n things in it, this one's 2n, and if I'm starting at 0, I can never get to the end because I still have another. I get to the end and it's just, well, there's still n more things. So I never actually have to worry about the looping back there either. Even if I had to, whatever. We could do that arithmetic, although that wouldn't work because then we would be overwriting things at the beginning. But the point remains, the arithmetic is still simple, but don't get scared by it. We can count by ones. Right? Right. So here's the idea right there. Now, we talked about idea 1, which was lab last week, terrible implementation. Idea 2 was, okay, well, we'll just keep track of the front, but we'll have to expand capacity more often, right? But we lose the linear time DQ and get a constant time DQ, so it's a win. But this is an even better idea, where it's purely amortized constant time, in Q, DQ. It's great. We love this. Cool. So will this implementation work? In Q, still constant time, potentially need to do an expand capacity, but no big deal. DQ, constant time, expand capacity. How often will the expand capacity get called relative to idea 1 and idea 2? Well, here, expand capacity relative to idea 1, probably about the same amount of time, right? As soon as it gets filled up, that's when we call expand capacity. Where idea 2, it should be less often, on average, because remember with idea 2, it's not so much when the array gets filled up, but it's after n in queues. Even if I had n in queues, n dqs, one more in queue, I need to expand capacity because I have all that wasted space out front, if you remember idea 2. Which was idea 3, but instead of looping back to the beginning, we just expand capacity whenever we need. Anyways, so this is just a better solution. There's a little bit more logic involved, but this is one of those cases. I remember last time I said like, oh, okay, sometimes good enough is good enough. This is an example of like, no, we could do better. Like this, it's not overly more complex where we get a lot out of it. But there are solutions to problems out there where we get really complex solutions, where we just squeeze out a little bit of efficiency out of it that really didn't matter, right? There's a lot of cost to code, not only in terms of runtime, but maintainability, scalability, how much can someone else understand it, and there's a lot there, right? The cost to develop it in the first place. There's a lot of costs that we have to consider. So let's implement it. Well, in Q, we might have to call expand capacity. Remember, we could have checked this too when size is the same as Q.length, or if rear and front are the same, that would also have worked here as well. I like this one more because I think it's a little bit more self-explanatory. Someone sees that, they're like, yeah, we're out of room. If someone sees when size equals rear and they don't know what's going on, they're left going like, why does that matter, right? You'd have to know more about this implementation to know why that matters. Where this is, I think, a little bit more obvious. So if we run in a room, we call expand capacity. Otherwise, Q to rear, next index of rear. What is this next index? This is just a function, or pardon me, a static method. I don't think I have it open. Yeah. It just does current index plus 1 mod Q.length. That's all it's doing. If you're like, why make a whole method for that? Because I think next index is, again, a reasonably experienced programmer would see this code and know what it does because it's common enough. But if you see a function called next index, or a method, a static, actually it's not even static, it could be, whatever. A next index, it's a little bit more obvious. Yeah?
It couldn't be static because he uses Q.length. So
you're right. I think actually that's a good point. I think that's maybe why, I think there was a time where I made it static and it took the Q length, and then I was like, but that's kind of stupid. Yeah. So I just made it a private method. You're right, good catch, very good catch. Anyways, I made it a private method because, I don't know, it's a little easier. If you look at that and go like, that's entirely unnecessary, fine. More power to you. So there we go, next index. This is just to hide that logic. And they go, rear is whatever the next index of rear should be. And then size plus plus, return true. Cool. What does expand capacity look like? Well, there's a little bit more to it than the other expand capacities, but the underlying logic is exactly the same, and it's what we talked about. Create a new queue of whatever, this weird casting thing, twice the size, from 0 to old queue length. Now you might say, well, hold on. We're starting at 0, but the old queue we might need to start at 1. You're right, but the same number of things will still be in there, right? Right? If there's 20 things in the queue, and 20 is the capacity, I don't care if we start at index 0 or index 18 or index 7, there's still 20 things in there. That loop's got to run 20 times. Just pay attention to what's where. New queue at I starts at 0. So we start at the beginning, go to the end. Old queue at front. Front, front's next index. Repeat. So we have another thing to keep track of, this front. Now, you might say to yourself, and maybe I should change this. Front is the field. And now I'm manipulating the field. Ugh. The field really is the front of the queue, and I'm now changing it. Maybe I should make an internal private variable, like an internal variable here to keep track of like where the next thing is and don't use front. Now, right now, by the way, I'm really getting into the weeds of like the spirit of what the code means. Functionally, this is fine. But using the field front to keep track of like, maybe that's kind of icky, right? Well, deal with it. It is what it is. Because at the end of the day, I still need to set front to 0. So there we go. But maybe I should change it, I don't know. And then rear is whatever the size is. Return new queue. But there's expand capacity. Was the point I made about front clear? All I mean is I could have made another variable called like old queue's next index instead of using front. And maybe that would be better because I'm changing the value of that field the whole time. But like if you think of this happening like instantaneously, which it doesn't happen, but if we think, you call the method, it does its thing, it's done. When it's done, front is fine. So it doesn't really matter, but maybe I should have done it differently. I don't know. All right, expand capacity. Yeah, there we go. DQ. If it's empty, otherwise get the element. Front is the next element. Sorry, front is front next. Like get the next index. Size decreased by 1, return the element. Equals. Here, this is what's kind of neat here. Is now, again, I don't care where you start. I don't like what you'll notice, here's what I mean. You'll notice that the value of I in here is not used. I is not used in this for loop, except for the fact that it's keeping track of I is less than this and I plus plus. It's just a variable to use to count how many times we've looped this loop. How many times should I run this loop? Size times. I don't care that I is 0 to size minus 1. I could be 1 billion to 1 billion plus size, right? Like I don't care. I'm just using size to keep track of like, okay, run this loop this many times. That's all. So I'm not making use of the I variable within here. What I am making use of is this is front and that's front. Though the two array queues might be equal, but one array queue might have a capacity of 1 billion, where the index of the front is 972, and your other array queue might have a capacity of 17, and its front is at index 0. That doesn't matter. What matters is that the elements are the same in order in the queue. That's what matters. I don't care where. Let me draw it. If I have an array queue that looks like this, an array queue that looks like this, and I have like A, B, C, and here I have A, B, C. The fact that this is the front of one, that's the front of another. This one has a capacity of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. The capacities are different. Doesn't matter for what we are defining equality. If I wanted to say like, nope, they have to have the exact same array capacities, I could have, but that doesn't really make sense. So I'm not going to. All I care about is that these are the same, these are the same, these are the same. So front will go from 1 to 2 to 3 here, and front will go from 0, 1, 2, 3, 4, 5, 6, 7 to 0 to 1 on this one. And that's what's going on in this loop. This front, that front. So this current index, that current index starts at the fronts. You check if they're equal. If they're not equal, return false, then they're not equal. If they are equal, keep checking to see if you find any inequalities. And every time you just update this and that next index with this dot next index. Now you'll notice you might say, oh, does it matter if I use this dot next index or that dot next index? It does. Why? Because of exactly what you said. This is dot next index will do mod its array capacity, and that's next index will do mod that's array capacity. Their array capacities would be different. If you're wondering, 0, 1, 2, 3, 4, 5, right? This one would do mod 5 to figure out its next index, and this one would do mod 1, 2, 3, 4, 5, 6, 7, 8. Mod 8. So we have to make sure it's modding the correct capacity to restart.
Mod 7. It's a capacity area.
Yeah, but no, it's still mod 8, because when it gets to 8, it would go back to 0.
And shouldn't the top one be mod 6?
1, 2, 3, 4, 5, 6. Of course, that's what I said. Good catch. Yeah, very good catch. Absolutely. So, yeah, there we go. So it is important which one of those next indexes we use, because we've got to make sure it's referencing their underlying arrays to know where to update the next index. These are all implementation issues. I had to do it this way because of how I implemented it. If you were to implement it slightly differently, well, then you would implement it slightly differently and do what you need to do in that situation. Cool? Cool. Any questions about the array capacity? Oh, and here's an example of using it. And again, this is like the exact same as the linked queue. This is the same code as the linked queue, except for the fact that we changed half of one line of code. Right? Cool. Although I think there's a slight difference, because I do explicitly make it size 5, and I've got this code here to be like, will it do expand capacity if I add more than 5 things? Anyways. Cool. Any last questions about queues? Nah, you're all experts. Yeah. Right? You're pros. Raise your hand if you're done assignment 3. Right? 1.5. 1 2/3? 2.5. Okay, cool. Right? So you're really pros in queues, right? Okay. The trick with assignment 3 is use the priority queue, which we talked about. So. All right, a bag. Now, a bag, you like this? It's like a Ziploc bag, right? If you couldn't tell what the design is supposed to be. Isn't that nice? So a bag is kind of like a stack, a queue, whatever. It's a data structure. Often it's a linear data structure, although it doesn't really matter. A bag is more of this, it's a more general idea than a stack and a queue, that's for sure. And they have more flexibility on how they're used. Like when you add an element to a bag or you remove an element to a bag, where? When you add something to a stack, the definition of a stack tells us exactly where it goes. And when you pop something, it comes from a very specific place. A queue, same idea. Very specific where you remove something, very specific when you add something, the front, rear, right? A bag, pause. When I say bag, you can really be thinking of a list in Python, okay? You could be thinking of a list. That's the idea. When you add something to a list in Python, where do you put it? Now, the lists in Python are a little bit like a jack of all trades, okay? You can really treat it like an array, or you can treat it as like some general data structure, whatever. We'll see that as we go. But long story short, a bag. You probably, like in 161, we didn't do this a lot, but you could be like, my list.insert and you specify an index, and it would add something in a specific index and like make room for it, right? Or you could be like index it equals whatever to like overwrite. So we kind of used it like an array or like a data structure where we call methods on it. It kind of was this nebulous data structure, where here we're going to treat it more like a general collection, like where we use methods to interact with it as opposed to indexing something directly. Anyways, little aside over. So a bag. Really a bag, in the most general sense, is just a collection of data where there really isn't even an ordering to it. It's just information that's there. Now, we will be adding, this is a high-level idea of a bag, and it turns out there are several different types of bags we might want to implement. So the high-level idea of a bag shouldn't really have an ordering to it. Now, the underlying implementation may have an ordering to it, like, well, if I put information in a bag, where am I going to put it? An array? An array has an ordering, but the bag itself doesn't really have an ordering to it. Think of like the priority queue example, right? The elements, when you dequeue it, like, did the elements have to have an ordering in the underlying collection? No. All that really mattered is that the elements came out in order. But how the data was stored didn't really matter, as long as it did what it did. Anyways. All right, so anyways, this idea of a bag. Now, like the other collections, we need a way to add things to it, remove things from it, get the size, check if it's empty, the classic data structure stuff we want to do. So given the more general idea of a bag, how exactly should this be done? It might not be that obvious. A stack and a queue, it's obvious because, well, the definition of those collections tells us how we use it. A bag is more of a whatever you want. Okay, store data in there. So when I say, okay, add information to a bag, where? Right? Where do we want to add it? When you add it to a queue, it goes to the rear. When you add it to a stack, you put it on the top. Add it to a bag, where you want to put it. Anywhere you want. How about when you remove it? Where should it come from? Right? The front, the middle, the end? The third one from the back after Tuesday? I don't know. It doesn't matter. What other potential functionality might we want? Well, look. With a stack and a queue, it had very well-defined uses. But with a bag, maybe we get a little more general. Maybe I should be able to access information at any arbitrary position. Update information at particular positions, check if a given element exists in a bag. There's a lot of things we might want to do with a bag. So the general idea of a bag is quite high level. And to answer these questions really depends. So to help determine how these ideas should work, we're actually going to implement two very specific types of bags. We're going to implement a sorted bag, and we're also going to implement an indexed bag. They're both bags, but they're less general. They're more specific ideas. I'm spitting a lot today, so if you're in the front row, I'm sorry. Really dry mouth, I guess. When we add something to a sorted bag, there's going to be some rules, right? When we remove something from a sorted bag, there's rules. When we add something to an indexed bag, there are rules. There's usage requirements. So a sorted bag, here's what it's going to be. If the elements must be sorted, how they are added and removed must be done very carefully. Okay, so we have a bag where the elements within the bag must be in order, based on some ordering that we define. So unlike a general bag, the specific kind of bag will have an ordering defined for it. All right? Although really the elements that have the ordering, but more on this in a moment. So the ordering of the elements will depend on right now. So the ordering of the elements depends on the contents of the bag. For example, some things that we have an intrinsic ordering to them. Now when I say intrinsic, that's just a fancy way to be like something in and of themselves that give you an ordering. Like integers, there's an ordering. Why? Because there is. It's harder, I don't know what else to say, there is. Why? Because we said so. There's an ordering, right? Does 2 come after 1? Yeah. Why? Because it does, okay? Because there's an orderedness to it. Strings in alphabetical order, there's an ordering, right? If I say sort these names alphabetically, well, there's an ordering. But I didn't really need to say alphabetically though, right? I could sort the strings in a different way. I could say sort the strings based on their length. I mean, that's going back to the numbers, but, but like the elements themselves will have an ordering that define it. So if I've got some collection that looks like this, so here's my sorted bag, okay? If I want to add something, so here's the front, there's the rear, whatever. If I want to add something to this bag, where does it go? Now with a general bag, it was like, I don't know, wherever we want. This is not a general bag. This is a sorted bag. So to be clear, we went from stack queue, very well-defined things, okay? Then we went to this, wow, a bag, what a crazy idea. And now we're right back down here. We're like, okay, but we're also defining a specific thing. So if I want to add the number 58 and I say, where do we put it? There's an answer. All right? Now, maybe there doesn't need to be an answer depending on how the overall implementation, but I think it's a good idea to have the elements stored in order. I think that's going to be a good decision here. So in terms of like what the bag means, where does the number 58 go? There is an answer to this question. Does it go here? How about here? Maybe I should say like, does it go here? No, why? Because 58 is bigger than 16. Does it go here? No, because 58 is bigger than 23. Does it go here? No, because 58 is bigger than 29. How about here? No, 58 is bigger than 40. How about here? No, 58 is bigger than 51. How about here? Yes. Why? Well, because 58 is less than 67. Well, how do I know it doesn't come even more before? Well, because I just concluded not one moment ago that it was bigger than 51. Because if it wasn't, it would have gone here. But because it is not bigger than 51, maybe it goes here, it's less than 67, okay, it goes there. So in order to find where it goes, we clearly have to do some form of search. And if there's n things, how many things we got to look at? And yeah, okay. But, still not too bad. The logic isn't crazy. And we know how to do a linear search. Start at the beginning, look at the next thing, look at the next thing, look at the next thing. Yeah?
So do these sorted bags extend the greater bag interface?
There must, we'll see in a moment, yes. Extends is a very interesting word choice, too. All right, so example of a sorted bag. So where does it go? It goes there. Why? Because it does. Why? Because the elements tell us the ordering. The bag itself doesn't really enforce an ordering. It's a property of the elements that give us the ordering, okay? Sometimes those properties are obvious, like there's an intrinsic ordering, like numbers. But if I gave you a bunch of pencil crayons and said sort them, you'd say, how? Because you can, but how? By their length, their color, frequency, spectrum, size, their color's name alphabetically. How do we sort these things? I don't know. If I collected everyone in here and said, let's sort us, how would I do that? By name alphabetically, last name, height, shoe size, hair length. It's ridiculous, right? But in order to do that, I'd need to tell you how to ordering it, and then it would be a property of the elements themselves that determines the ordering. Okay? I'm going to sort by this, and then each thing has that property that tells me where to put it in the ordering. Yeah? Yeah. And then an indexed bag. This is going to be more similar to what you're used to in Python. Indexed bags are where elements can be referenced by specific numeric position, like an array index, okay? This is just like lists in Python. The specific kind of bag will have an ordering. So, okay, the element positions are important. So there's an orderedness to the elements in if I put elements in the array, like A comes before B by virtue of being at an index 1 and index 2, not because these elements were in that, not because B alphabetically is, more than A. That's not why they're like this if this was an index bag. It's just by virtue of the index that they're in. So the underlying collection kind of determined the ordering, but the elements aren't sorted. Does that make sense? Right? Like if I have a triangle, circle, square, happy face, Christmas tree. Right? There. Right? Circle doesn't come after triangle because it comes after triangle based on its like, well, circles are greater than triangles. Well, no, that's ridiculous. Why did it come after? Because it's an index 1, and this is index 0, and this is index 2, 3, and 4. So the order of the elements is arbitrary, but there is an ordering because 0 comes before 1, which comes before 2, which comes after, right? Yeah. So this specific kind of bag will have an ordering, but the element position is important. The elements are not sorted based on some property of the elements. User determines the ordering of the elements based on how you add them. So every time an element is added or removed, the indices may need to change. Like if I added this light blue square here, that would become index 0. This would become index 1, and so on. So after this, it would look something like this. So, where the elements are, their indexes might change. Because I could say, add this at index 3. So that would become the new 3. This would have to make room for it, and so on. Yeah? Yeah? Yeah. Now, functionality. What might we want to do? Well, okay, let's take a step back and think of the bag. So a bag interface will be kept simple. We want a way to add an element, remove a specific element, check if an element is contained in the bag, like return true, false, whatever. Count the number of occurrences of an element. So like how many 7s are in this bag, right? Check if it's empty, get its size. Get an iterator for a bag. More, I'm kind of teasing a spoiler, or teasing something we're going to see in a moment. More on iterators later, but long story short, an iterator is a handy tool, a general purpose tool for how to iterate over a collection, regardless of the underlying container. Remember how you iterate over an array easily with like a for loop? But for loops aren't great for link structures. We use that like current equals current.getNext. An iterator is a tool to make the way you iterate the same, regardless of the underlying collection. It's pretty handy, but spoiler, we'll see this shortly. Extends iterable, what's that? That's for the iterators. If your class extends, notice that it doesn't say implements. This is a new keyword. Extends. What? I know. It's a new keyword that says it's going to act very similar to an interface in that like, oh, we have to implement something called like iterator that returns an iterator. But more on extends shortly. We're going to learn about it in a different context pretty soon. So what's the bag interface? Add Boolean, true, false. Remove Boolean, contains, count, is empty, size, and this iterator thing. Right? We want our bags to return an iterator. By extending iterable, now Java knows that you can always iterate over anything that is in fact a bag. But this is an interface, not a concrete class. Cool. Any questions? I know I'm doing some hand wavy stuff about like just trust me. You'll see in a moment. Okay, so I went from talking about bags to indexed and sorted bags, and now we're back to talking about bags. Yes, because an indexed bag and a sorted bag are both bags. I know. They're both bags. But not quite in the same way that like an array queue and a linked queue were both queues. Like array queues and linked queues were both queues, but array queues and linked queues were concrete classes. Those were implementations of a queue. Okay? So they're both queues. They both can do everything a queue can do. But I'm talking about something a little bit different, because when I say sorted bag and index bag, I'm not talking about any concrete implementation yet. There's no arrays, there's no link structures. I'm just talking about these ideas. And an indexed bag and a sorted bag, they're both bags. And they should do everything a bag can do, but there might be some special rules or additional functionality required for a sorted bag, and similarly for an indexed bag. But the additional function, like, okay, they're both bags, so I want them to be able to do anything a bag can do. But my indexed bag, I want to be able to like get an element at a specific index. I don't want to do that for a sorted bag. But I might want to be able to like when I add something to a sorted bag, it's got to act a special way. So they have things in common, but they are unique, and they are not a concrete implementation. Okay? So what we're going to say is, okay, let's start to define a sorted bag. A sorted bag will be a bag. It can do anything a bag can do, but I want my idea of a sorted bag to also preserve that very special sorted property. Whenever I add anything, it's got to be still sorted. I want to be able to like remove the first element, remove the last element, get the first element but leave it alone, get the last element but leave it alone, you know, kind of like first and peak, right? So that's also what I want here. So now you're going to see a lot of crazy code in here, some of which is going to be magic for us. I'm sorry, it is what it is. Half the reason it's magic is half of it's magic to me too. But what does it mean? Okay, so let's focus on what we do know. Public interface. This is an interface, not a concrete class. Name of the class. What? And then, okay, extends bag. Okay.
Amazing.
So let's focus on everything except this right here. This just says, I will talk about it in a little bit more detail, but this is basically like the elements of type T has some special rules. It can't be anything of type T. It has to be things that have an ordering, because it's a sorted bag. You can't add things to a sorted bag that don't have an ordering to them. All right, so public interface sorted bag, magic, extends bag. What that means is basically all of those methods that were in the bag interface are copy and pasted right here. We don't see them, but they're there. In the exact same way. This is called inheritance. Okay? We inherit the methods from the parent class or interface or whatever. In this case, this is the parent. What is the parent class of every class no matter what? Or like the super duper parent?
Object.
Object. Exactly. Remember how like you inherit like equals for free, a toString for free. Whether you implement them or not, you get them. They're not that helpful, but they exist. Now you are inheriting from a concrete class, meaning you get the concrete actual equals implementation. Now this is an interface, meaning when I inherit the interface's like size, okay, there's no actual concrete implementation there. It's an abstract method. It's just the name. But there is an int size in here. You just can't see it because we inherited it because we said extends bag. So it is there. If I ever go to implement, the interface sorted bag and make like an array sorted bag, I have to implement all of these methods, but also everything from the bag class, right? Because these do exist here, like it or not. If you don't like it, well then don't extend it. But that's what we want to do here. Okay? Yes?
In the last code example we have, you did extend iterable.
Yep.
So that's the same idea.
It's the exact same idea. Yes. But don't worry about that one right now. But it did use that exact same keyword idea. Yeah?
Wait, so if you have to also implement all the stuff in the bag, why is there a second add?
It's not a second add. It's an override. So this one's actually really special. Now, does this serve any functional purpose? No. But it serves a purpose to inform the user of this interface. Why is it first of all, it's an override whether or not I put this little tag there. That tag doesn't have any functional difference. It's just an indication to the compiler, but also to other programmers to be like, oh, this is overriding from some parent class. Okay? And you go look at it, but you'll notice like remove first and remove last, they're not in here. but Boolean add is there. I could have like a int add t element. I could like do integer add t element, and it wouldn't be override because it's a different signature. Because the return type is different, that's fine, right? But why is it an override? Well, I put this here because if you go open up the Java docs, which aren't included here, it's saying add, but hey, when you add, you have to actually add such that the order of the elements are preserved. That's why. Because otherwise, the general add, someone might be like, where to add? To the end, like append. Makes sense, right? Where here, it's like, well, you know, the Java docs, add. And it's really there, so the Java docs, if someone were implementing this and they looked up the Java docs for add, they would see the Java docs for the sorted bags that would be written there. That says like, okay, add, but here are the rules about how add should work. It adds it such that the elements ordering is preserved. So it's an override. Will it have any functional difference? No. But it has a giant difference in terms of like the overall design and intentionality of what our code is intended to do. And it's like self-documenting code. That's why. It's like a super comment, where like the comment is like in the code in and of itself, which is what we want, right? We want our code to be self-documenting. We want our code to be as clear as possible such that it like explains itself. We use comments sparingly because if you have to write like a lot of comments in your code, maybe you need to rethink and rewrite your code such that it's more obvious. Sometimes it is what it is. You just gotta it's a complex chunk of code, you gotta explain it. Other times, maybe you can kind of rework the code to be a little clearer.
Also, if you had like an array bag that was like a proper class, then you could extend that, or sorry, you could have array sorted bag, extend array bag, and then the add method there would overwrite the original one.
Yes, but even without this,
no, yeah,
but yes, absolutely.
So it needs to be in there, so it wouldn't.
So it wouldn't call the superclasses, yes, because otherwise, that's a good point too. Now, it doesn't apply here because these are abstract class. They're interfaces. There's no concrete class here. But his point was really interesting. Is imagine imagine bag was a concrete class with implementations and everything. There's a reason why, in general, we don't extend concrete classes. That creates issues. But if we did, which we can totally do, if add was a concrete method, and then we extended, we would definitely want to override that add to be the one we want. In the same way that we override the equals that we get from the object class, because the equals from the object class is often not that helpful. Same with the toString, hash code, etc. Cool. Great chat. Now, what on earth is all of this? Now, I think I explain it. All right, so notice that despite wanting all the bag methods, they are not included in the sorted bag. This is because sorted bag extends bag. The extends keywords means that this interface class will inherit all the methods being extended. Bag is being extended in this case. Similarly, the type T is extending comparable. T extends comparable, which is a generic type. I don't know what super T, what? So this will be discussed in more detail later. Long story short, it means that the elements T that we have in here has a restriction. It's generic, but the elements have to have an ordering defined for it. And that's kind of like, it needs to be the elements need to be comparable. All right? That's what that means. They might be comparable, but it needs to be defined. Like if I say, okay, add a pencil crayon. If pencil crayons have a comparable for it, meaning that there is a well-defined ordering for your pencil crayons, whatever you want it to be, have added. But if it doesn't, I can't add pencil crayons to a sorted bag because how the hell do I sort it? So there's a restriction on the type. Yeah?
What dictates what counts as comparable?
We do. Now, some elements in and of themselves have an ordering defined for them. Other times we need to go in and be like, hey, there's the ordering. Think of it like equals, right? Some elements have equality defined for it, like integers. Why? Because they do, right? So whoever made Java said, okay, integers that are equal, they're equal. Okay? Now, if you go make a class like a country, what does it mean for them to be equal? right? And then we had to say, okay, if all these things match. Then I might ask you the question, if I gave you one country and another country and told you to put them in order, how would you do it? Sometimes you have an answer. You could be like, well, population size. Okay, there, good. But you had to decide that. Java goes, what do you want? And you say, this is what I want. And you write the code to do it. In the same way that you write the code to define equality. Yeah. Yeah.
And how do you like do a concrete implementation of this? Like, do you need to like actually like state how they're comparable?
We will. I'll show you very shortly.
Is it within the bag or something you do?
You'll see. You'll see. There's a couple of ways, but you'll see. You'll see one way of doing it in class, and then you'll see a different way of doing it in assignment 4 that are very similar, but they have different use cases, but the ideas are generally the same. Yeah?
Like hashing?
No, not at all. No. But like hashing in the sense that we need to tell our class, hey, if someone wants to hash you, how? That's how it would be similar, right? But in terms of the ordering, actually, maybe it depends on what you mean by similar. Like, we could order these things based on their hash value. I don't know really, we could. We get to make it up, right? So, I guess kind of related, I suppose, but yeah. It's related, but be careful on trying to connect too many dots there. All right, so yada, yada. All right, although not explicitly included in sorted bag interfaces, the methods from bag are still part of what defines a sorted bag. Why? Because we extend it. The sorted bag cannot be implemented without implementing all the methods from the sorted bag and the bag. An idea of inheritance will be discussed in more detail later. And then we have an index bag. Similar to a sorted bag, let's make an index bag. In addition to the bag methods, what else do we want our index bag to do? Well, add an element at a specific index, remove an element from a specific index, change or like update value at a specific index, get the element at a specific index, find the index of a specific element. A lot of things that you just might want to do with a general purpose sorted collection. What's nice about an index bag is if we implement it, you can use it in all the places where you use an array, but then never worry about running out of room because presumably the index bags will expand capacity, which is nice, right? And then if you're like, well, Java already has something called an array list. If you can't connect the dots yet, though, that's what we're building right here. Yeah, an array bag isn't an array list. Technically, there's a definitional difference between bag and list that Java's kind of pushing, but it's really kind of, I'm being an asshole when I bring it up. All right, so index bag, overwrite add, okay? But we have another add where it's not overriding, but I specify the index and the element. Now, we have, maybe it doesn't come up here. There is a funny peculiarity that can happen when int index, and what if t is like an integer and then they're both integers? How does it resolve the types? You know what, we'll cross that bridge when we get there. Here's the interface, add an element, but we also include a specific index. Set, get, remove, index of. There we go. Remove, this actually has a different signature from the inherited one, so it's not an override. If we look at this one here, remove just returns a Boolean, and it takes an element. Here, this returns the element and takes an index. So that means our index bag will have 2 removes. Which one should you use? Whichever one you want. Do you want to remove a specific element, or do you want to remove something at a specific index? Depends on what you want. Cool? Cool. All right, I'll see y'all tomorrow, right?